Thank you so much, Drew, for the introduction, and I want to thank James for the invitation and the opportunity to speak here today. So I'm going to change slightly the tenor of my talk. So it'll still be about essentially, applications in light harvesting using polaritonic systems, so strong light matter interactions. So looking at energy transfer in optical cavities, but going towards a more sustainable and more bioinspiration theme. So something following on from some of that quantum biology, perhaps, that we saw this morning. So I'm coming from the University of Melbourne and the School of Chemistry, but I've also been heavily involved recently in the Hutchison Science Centre of Excellence. And one of the things that we're passionate about at Hutchison Science is really sustainability. Well, first of all, making optoelectronic devices better. So things like our photovoltaics and our light-emitting devices, making them more efficient, so making them lighter, perhaps more flexible, and more efficient, of course, but also maybe making them more sustainable. So thinking about whole of life. What do we do when our solar cells stop working? Are they recyclable, and so on? So we've got a couple of tools that we can sort of play with there. First of all, we've got the chemistry bit, so we can play with the materials that we're going to put into these devices. But secondly, we've got the light bit. So often in these devices, we've got multi-layers, so we can have multiple sort of reflections between these layers of different refractive index, so we can get constructive, destructive interference. So maybe we can use tricks with light to make these systems more efficient again. So for example, if we're doing photovoltaics, maybe we can ensure we get perfect absorption in our device. Or maybe if we're looking at light-emitting devices, we might use surface nanostructuring, for example, to modify how light is extracted out of these devices. So again, to make them more efficient. All right, but what we've got then is, with our materials, normally we've got these very, very strong or very good chromophores, so molecules that are interacting strongly with light. And also we've got light bouncing back and forth between these layers in the system. So we've got chance for reversible interactions, or reversible light matter energy transfer, and strong light matter interaction and polariton formation. And I think I can skip through much of this introduction because I couldn't make it, unfortunately, till today, but I've seen from the conference schedule that we've talked a bit about polaritons towards light harvesting already. But essentially, when we take our molecules and put them inside a simple photonic micro or nanostructure, such as this Fabry-Perot cavity, then instead of having our sort of one-way spontaneous emission when we excite these molecules, now we've got a chance for the emitted light from these molecules to bounce back and forth between the mirrors and hopefully be reabsorbed before there's any loss process, and therefore we can move into this ringing regime. We get Rabi oscillations and generation of strong light matter interactions and polariton formation. This one's going to come up. Oh yeah, so, well, I don't have to play. Again, this is more I often talk in front of chemistry audiences, and so this is but something that probably most of the people in this room did as an undergrad physics experiment. So, one of the I guess most interesting consequences I'll just come back here. Interesting consequences of these strong light matter interactions when we have lots of, sorry, got this all messed up. When we have lots of molecules in a cavity, is that we're going to get reversible interaction between the cavity photon and a superposition of the excitation on all of these molecules. And so we're going to get we're going to drive coherent interactions. And that has, makes one think about, now we're driving sort of in-phase behavior of molecules that are now really far apart, well beyond the Forster limit. So can we think about new ways that we can move, for example, energy or even charge inside a system like this that we could incorporate into an optoelectronic device and make it more efficient. So that collectivity is a really important theme. So of course that ringing behavior is very fast, particularly in these lossy metallic mirror optical cavities. So this is happening in tens of femtoseconds. So usually we're going to be using the frequency transform of that, looking for the Rabi splitting in the frequency domain to characterize our polaritonic states in these systems. And I suppose the thing that I've been interested in the last 10 years is really taking this, quantum, I suppose, a QED picture of strong light matter interactions, and then sort of mixing that with a classical Jablonski diagram that we'd use in molecular photochemistry, and thinking about the consequences of generating polaritonic states in chemical in chemical systems and things like optoelectronic devices. All right, I'll just skip forward. This is slightly out of... And so as I mentioned, so now that we have these interactions, these really now collective long-range interactions between molecules inside a Fabry Pro optical cavity, can we think about new ways of doing energy transfer, for example, over much larger distances than you would by force or energy transfer? And so we can think about these kind of systems where we have a forced donor and an acceptor separated by a spacer that might be tens or hundreds of nanometers thick, so well beyond that forced limit. And indeed, we can demonstrate enhanced energy transfer in those systems. So originally, we took this nearly 10 years ago now, sort of to the 100 nanometer limit. So we could, again, by coupling this donor and acceptor via a cavity photon, get those very long-range interactions. Now that's been taken out to at least the micron range, so using polaritons to get communication between donor and acceptor, energy transfer over many microns. We can also think about doing the same thing with electrical conductivity, but maybe in using plasmonic structures in the 2D configuration. All right, so those are the motivations. So then just coming back to this slide here, so now what we can think about doing is taking optoelectronics, adding these polaritonic structures. And so we go from optoelectronics to polaritonics. Lots of work here. So originally it was really targeted a lot towards polariton lasers, but now people are showing that you can make solar cells more efficient, LEDs more efficient by incorporating these polaritonic resonances. Also a lot of work, again, that as I mentioned before, that mixing of that Jablonski diagram for molecular photophysics with that quantum electrodynamics of picture of polaritons, also changing other aspects of molecular photophysics and even chemistry is a big area that we've been involved in. All right, but most of these structures tend to use, I would say, well, things like, for example, metals, which are environmentally difficult for us to obtain and purify and the like. So can we think about incorporating now sustainability into this polaritonics game? And let me just move past here. And so this is sort of taking me to where I want to focus on today in my talk, looking at sustainable and bio-inspired optical cavities for strong light matter interactions. Came about when I joined this Bioinspiration Institute at the University of Melbourne, and that brings together, well, not just chemists and physicists and biologists, but also architects and even artists, all coming together to get involved in bioinspiration, which is the idea that we kind of make a shortcut. We take all these billions of years of problem solving that nature has undergone to come up with solutions of living here on Earth. We just take a shortcut and borrow those ideas. And so here's the team, the bioscience team that I really want to acknowledge. So Professor Debbie Stewart-Fox at University of Melbourne particularly, and her postdoc now, Laura Espinoroso, and my students, Sam Brook and Jianfei Yu's done a huge amount of this during her master's talk. So what is this bioinspiration about? Well, you may be walking in the Swiss mountains and you get burrs stuck on your pants and it's kind of troublesome, right, and annoying, but then you might have the idea of Velcro, so that's a story that really happened. Here's a story that kind of, I'm not sure this has actually happened yet, but Gecko has been a massive inspiration for people like Tom Cruise, climbing buildings and like. I don't know if this is actually real yet, but I think I've seen things along that direction. All right, so what were we looking at? First of all, we started to look at some local beetle species, on the east coast of Australia, and they're the Christmas beetles, and they appear about this time of the year. You're most likely to see them. So these beetles, they are one of the most successful family of insects on the planet, and they're successful because they've got this hardened outer wing called the elytra, which can be multi-layered and have a photonic crystal kind of structure. So, it's important for them for protection, but it also gives them lots of ways to interact with light. So not only do they interact with visibly, so they can play with the color via interference effects of light on their elytra, but what was interesting, we were just interested in what they were also doing in the infrared. So some of these beetles really reflect most of the near infrared, whereas some of them absorb a fair bit of it. So, and was that to do with sort of passive thermal regulation? So for the first part of this, originally we were interested in developing kind of, passive cool coatings, maybe, invisible infrared signatures, using these sort of sustainable materials and inspired by these beetles. So in doing that, we spent a lot of time characterizing the iridescence of these beetle structures, and they're really quite beautiful iridescence. So here we've got just reflectance as a function of angle here, and so we can see here we get a red reflectance coming straight off the beetle, and then at higher and higher angles, of course, we get dispersion, we get the orange and the green reflection. It's even more amazing or exciting than that. So they are. We can take a cross section with an electron microscope. We can see these effectively multi-layer structure here. So it's a Bragg reflector, but with a twist. So it's made actually of chiral, so these are literally made of chitin, so it's a hardened polysaccharide, but it's made of these rods which kind of spiral down. And so not only do they have this beautiful iridescence, but it is almost perfectly left circularly polarized. So amazing materials in themselves. And it got me thinking, someone who'd spent a lot of time making synthetic optical cavities to generate polaritons and strong light matter interactions, maybe we could have a look at harnessing these materials to do the same thing. And so just in a very short story, here's just an example of that. So again, this is this iridescent or dispersive reflectance of that Bragg structure on top of that beetle. So at normal incidence, about 650 nanometer reflectivity. So we grabbed the dye methylene blue, which has a strong absorption resonance right at that wavelength range, and we could soak that dye into these structures, and you get something that generate a polaritonic signatures, or something that is essentially a Bragg polariton, or I've seen something called a Bragg oraton, something in the literature. It's a bit of a mouthful, but you can see here we got that splitting that we expect in the reflectance, and also you can see the flattening out of the dispersion, so the increase of the effective mass of this quasi-particle as the light interacts with the material. So there we go. We've got inspiration here already that maybe we can indeed have sustainable solutions for polaritonics. Don't need to have metals or anything around like that. The other interesting thing, which is still to be done, is to look at potentially in chiral induction of emission of this methylene blue, which is non-chiral, but maybe it's been templated as it's gone inside these beetle shells. So we're also making sort of synthetic versions of those beetle shells at the moment. All right, so those beetles, they just have that structural color, right? Those interference effects, but they don't generally have much pigment in their systems evolved naturally. But what we thought we'd do after that was kind of go on the search to see if we could find creatures that had co-evolved both pigment and that structural color in the same environment, or in other words, had they naturally evolved polaritonic systems. So which would be another nice example of quantum effects in biology. So we were looking for these split kind of spectra, and it turned out the beetles are not too interesting. Couldn't find a lot of co-evolution of the pigment and the structural color in the right way. The butterflies are much more exciting. So generally speaking, we were looking for these kind of split reflection spectra associated with some strong dye absorption in the system. We thought these graphemes were the go, but then, as often turns out, when you have a close look, it turns out not to be the case. So they have basically a white light reflector underneath, and then a pigment layer separated on top. So it's more or less a trivial filter effect in that case. So there's no strong light matter interactions possible there, as they're too separated. But then we went on to, I would say, a more local butterfly species. Well, the graphemes all through Asia as well, but these birdwings, which are the world's largest butterflies, are really sort of endemic to Australia and Indonesia and Papua New Guinea. Again, we've got these split reflectance spectra and a dip here that's associated, which I'll show you, associated with a pigment. So potentially here we could find naturally evolved polaritons. The other interesting thing is when we look in a cross-section of the scales, the wing structures, so there's a structural color here, which is essentially a multi-layer underneath here, which has got air and chitin layers. But we can take a fluorescence spectrum here. Well, this is other people's work, and they show this fluorescence all through the structure. So we've got our pigment, we've got our structural color in the same spot. So this is where we want to look for to see if we can see naturally evolved strong light matter interactions. So we grabbed our local birdwing, which is the Cairns birdwing, so obviously coming up from Queensland. Obviously, it's got these beautiful colour patches, blue, green and yellow, and if you zoom in, you see those colour patches are made up of sort of tens to hundreds of micron size scales that give the colour here. And so the question was, well, where's the pigment in these systems? So we could just put them under a UV lamp and see where the fluorescence comes. And you can see the yellow patches here are highly fluorescent, the blue patches and the green patches, not so much. So the pigment's going to be localized in those yellow scales. And it's a nice, strong fluorescence sort of in the yellow. All right, so then we could take reflectance versus angle spectra of these systems as well. So one of those green scale or patch scales where we know there's no pigment and we get a dispersive reflectance sort of going from the yellow down to the blue-green, whereas that yellow scale where there was lots of pigment, we see a very different behavior. So we've got this very strong dip here and we get a dispersion and what looks like essentially an avoided crossing occurring here. So we've obviously got a strong pigment absorption here. We get dispersion of that reflectance there, an avoided crossing, and then appearance up here of a second peak. So that splitting that's very characteristic of polariton resonances. We're fast running out of time. So now what we're going to do is kind of deconstruct this to prove these things to ourselves. So first of all, how do we get rid of the structural color so we can just characterize the pigment where we can just put some refractive index matching oil, fill up these air holes. So we go from green to dark. We've lost our reflection. We can then take a transmission spectrum and get an absorption spectrum of our dye. It'll look a bit like this, so a strong absorption around about 480 nanometers. So we characterize the pigment. And then secondly, we wanted to remove the effect of that pigment. So the best way we found there was actually just to photo bleach with a laser. So a strong laser at that 480 nanometer peak. And we could burn down the fluorescence. You can see collapse of that two-peak reflection spectrum to a single peak again, which you'd expect if you're going now out of the strong coupling regime. And the other nice thing is that originally were kind of yellowy green color before irradiation turns sort of minty blue, which is exactly the color of these butterflies, of this butterfly genus, the ones that don't contain pigment. So we're pretty happy that we got rid of all that pigment. Well, I don't have too much time to talk, but so essentially we've got strong light matter interaction, but we never get to quite a 50-50 mix because the dye resonance is at about 490 nanometers, whereas the structural color only sort of disperses to about 510 nanometers. So we might have a 60-40 mix of light matter mixing there. All right, I'll quickly finish up. These are just some helium ion microscope images now, just to show that the actual structure is really an inverse opaloid structure. So there are these air holes in a chitin sort of matrix. And so it's nice to see that, well, essentially nature has mimicked something which we did in around about 2001. So this is someone looking at sort of self-assembled microspheres of silica, so an opaloid structure, and then putting molecules around it and inducing strong light matter interaction. So, but of course this butterfly has already been onto it. So just a sort of a quick word on sort of origin stories of polaritons. So exciton polaritons, I think we talk about the early 90s as the genesis of this, and happening in Japan and in Europe, but maybe we can start to redefine that. And so it's in these Ornithoptera species that I've been working on. So you can see that maybe the story began in New Guinea and Northern Australia a lot longer ago. Just one more minute if I could. So that's a sustainability story, but the other thing we have to think about if we're going to make polaritonics real is, well, another trend in optoelectronics is to go towards sort of wearables. So how do we, can we imagine these things incorporated into things we can put on our body or into our clothing and the like? So very recently, just quickly, we've been looking now at PET films, about 2 microns thick. We coat them both sides with gold, so now we've got a freestanding flexible optical cavity. And then looking at what would happen when you stretch these systems. So here we're looking at stretching from 0 to 20%. So you can see we get blue detuning. So we thin the cavity as we stretch. So we get blue detuning. You can see we have a gradual degradation of the Q factor of the cavity modes as well. But the nice thing is if we look down right in the infrared here, so for these 2 micron films, we have an optical cavity mode around about 1700 per centimetre, which matches to the carbonyl absorption of the PET film. So we get strong light matter interactions here. Unstretched, we're kind of out of resonance here, but then as we stretch from 0 to 20%, we can stretch right into resonance. So we've got stretch tunable vibrational polaritons. But I think the story here is that you still, even with around 30% stretching, which is what you'd expect, which kind of would be a maximum when you're wearing your clothes, you still more or less stay in a strong coupling regime. All right, I'll just acknowledge Engan Akinoglu and Dali Kwan for that work in my labs, and otherwise, thank you for your attention.
Thanks, James. I think we might have time for one or two quick questions. Any questions out there?
Hi James, thanks for the good talk. I was just wondering, on top of all this sort of looking at the biomimicry, can you learn anything about different ways to fabricate these sorts of structures? Obviously butterflies don't grow in a CVD machine.
Yeah,
There's
exactly.
got to be some other method of making these. Can you take anything away from that as well?
Yeah, so we've started that more with the beetle structures. So obviously multi-layers are something we can do, spin coated or spray coated, but yeah, those chiral rods is something that I think we'd have a lot of trouble, synthesizing in the lab. So that's something I'd like to look into, but I reckon it's a huge challenge. That's a self-assembled structure that we're probably a long way from being good at making. Yeah. Cheers.
So you mentioned the chirality. You haven't done those measurements, but do you think you're going to see some polarised?
Yeah, unfortunately, I haven't done them. I've been talking about doing it for a while. Yeah, I imagine we would. I mean, again, these polariton states, you hybridize all the properties of the molecule and the light. So we've got that chiral photonic mode. It should be sort of imprinted on the polaritonic state. So I hope, I'm confident we'll see that. Yeah, but.